Welcome to Chemistry Buzz. Again, I welcome you to my third video on degree of freedom and Gibb's phase rule. In my earlier video, I have discussed the phase and its determination. The phase is designated as capital P, component designated as a capital C is equal to N minus E, the relation we have used for its computation. And today we will learn degree of freedom. The phase, component and degree of freedom, these are the basic fundamentals of the phase rule, basing upon which we can proceed deep into the chapter. So far as degree of freedom is considered, we have read it in the kinetic theory of a gas, and again we are going to read it in the phase rule. So what is the similarity and difference in these two chapters? In the kinetic theory of a gas, the degree of freedom, the number of independent variables used to explain the state of the molecule. And in the phase rule, the number of independent variables such as temperature, pressure, concentration used to define the system completely. Okay? So, the degree of freedom is the number of independent variables such as temperature, pressure, concentration, which must be specified in order to define the system completely in case of phase rule, and in kinetic theory of a gas, define the molecule, state of the molecule completely. So the basic fundamentals of degree of freedom is same. So how can we understand physically what is the degree of freedom is? So let us consider a gaseous system. Say in this container, 2 mole of gases are taken, and it is enclosed with a piston. Okay. So to define the state of the gas here, we need 3 variables, say P, V, and T. So these are called the state variables. State variables. Okay? But to define the state, we need 2 variables. Say we can take PV or VT or PT, any 2 variables we can take, and we will determine the third one using the formula PV is equal to NR. Okay. So using this formula we can calculate the third variable. So these two are called independent variables, and the third one which we obtain from this relation is the dependent variable. So the number of independent variables in this case is 2. So number of independent variable is 2. So the degree of freedom is equal to 2. So let us consider another example. Suppose I have this duster. I want to determine its potential energy. So to determine potential energy, we have the formula, that is V is equal to mgh. So its mass is fixed, and acceleration due to gravity is fixed, and the only variable is, that is, its height from the sea level. If it is known, then we can calculate the potential energy. Say this is the potential energy curve, and say this is the height from the sea level, this point or this point. So at any point, if the height is known, we can calculate the degree of freedom for this duster. the potential energy of the duster, and the degree of freedom for determination of potential energy of this duster is 1, because it depends upon the only one variable here. Okay. So now consider another example in which in a container we have taken water and it is covered with. So after some time there will be equilibrium between water and water vapor. So when water and water vapor are in equilibrium, there are two phases in equilibrium. Here it was one phase, and for particular temperature there will be the vapor pressure is fixed, and for particular vapor pressure the temperature is also fixed. So we need one variable to define the equilibrium. We need one variable. So when T is equal to 40 degree, there will be certain vapor pressure, and when it is 50, there is also another value of vapor pressure. And when T is 100 degree, it is the boiling point of water, and the pressure will be 1 atmosphere. So that is fixed. Okay. So if one is given, so other one will obtain. So one is a independent variable in this case. So the degree of freedom in this case is 1. So F is equal to 1 in this case, and P is equal to 2, and C is equal to 1. This is a one component system. Now consider the more specific example, that is the condition in which ice, water and water vapor, they mutually coexist. That means the three phases coexist. So the three phases can only coexist at a particular condition. Okay. So when the condition will be slightly changed, the point will be vanished. One of the phases must be vanished. So that point is fixed. So that point is invariant. So this is, in this case, the degree of freedom is equal to 0. That point is invariant. It is condition. The three phases will be at equilibrium. That is condition. So the degree of freedom is called invariant. The system is not depending upon any of the parameters or any of the variables. So the degree of freedom in this case is equal to 0. So now let us use the Gibbs phase rule. So what is Gibbs phase rule? The Gibbs phase rule, it is the relationship between the phase components and degree of freedom. Okay. So it is the relationship between the phase C minus P plus 2, F is equal to C minus P plus 2, or we can write also this F is equal to 2 plus C minus P. So using this form, there is no risk. But using this form, there is certain risk, because sometimes students perform the T plus 2, they add and perform the algebra and they get erroneous results. So here we have separated the plus and minus, and there is no risk. We can, so in our calculation we will use this one. So this is no different from this one. Again, so now let us use this formula, Gibbs phase rule. This is Gibbs phase rule, and the formula is given. And now let us use this formula for these three systems, and using this, how we are able to predict the degree of freedom. So this is a gaseous system. The phase is equal to 1 in this case. So this is a gaseous system. The phase is equal to P is equal to 1. The component is equal to 1. So the degree of freedom F is equal to 2 plus 1 minus 1, that is 2. So the degree of freedom is 2. So using this formula we obtain the degree of freedom is 2, and from considering the basics we have already obtained the degree of freedom is 2. The dependent variables and independent variables we have separated here. And if consider the water vapor and the water equilibrium, here where the phase is if P is equal to 2, component is equal to 1, so the degree of freedom F is equal to 2 plus 1 minus 2, that is 1. So same thing we are getting. So we have calculated here from the basics, that is the degree of freedom is 1, and here the ice, water and water vapor are in equilibrium. So for in this case the P is equal to 3, C is equal to 1, so F is equal to 2 plus 1 minus 3 is equal to 0. So when it is 0, degree of freedom is 0, it is invariant. Okay? So when degree of freedom is 0, it is invariant. So when degree of it is called, so when the degree of freedom, so when degree of freedom, when degree of freedom F is equal to 1, it is called monovariant. F is equal to 2, it is bivariant. And F is equal to 3, sorry, F is equal to 0, it is invariant. And when F equal to 3, it is trivariant. Okay? So in the gaseous state, this one phase, that is a monovariant, two phase, the degree of freedom is 2, so that is bivariant, and the triple point, the ice, water vapor coexist, that is invariant. So here what we have seen, when the degree of freedom, the phases, here the P is equal to 2, here P is equal to 1, and here P is equal to 2, and here the P is equal to 3. Okay? So what we have seen, when the number of phases increases, the degree of freedom decreases. Okay? When the number of phases increases, say we have taken phase that is 1, 2, 3, and the degree of freedom here, that is 2, 1, 0. Okay? So when the number of phases increases, the number of degree of freedom decreases. So how can we correlate the maximum phase and degree of freedom? So when P is maximum, F is minimum. The degree of freedom is minimum. So when P is maximum, the F is a minimum. So let us say F is minimum. So F minimum is equal to 0. So what will be the phase? We have F is equal to 2 plus C minus P. So the P max, P will be maximum. So 0 is equal to 2 plus C is equal to C minus P max. Or we can say P max is equal to C plus 2. Okay? So P max is equal to C plus 2. So again, when the degree of freedom will be maximum. So F minimum here we have taken. So F max, so when F max, P must be minimum. When P minimum, the P is equal to 1 because P cannot be 0. Why? If P is equal to 0, then the system will vanish. If there is no phase, there is no system. So P cannot be 0. So minimum value of P is equal to 1. So we can write this F max is equal to 2 plus C minus 1. Okay? 2 plus C minus 1 because the P is the minimum. So this is equal to C plus 1. So F max is equal to C plus 1. We have figured one more relation. F max is equal to C plus 1 and the P max is equal to C plus 2. These are two relations in addition to the Gibbs phase rule. F is equal to 2 plus C minus 2. Okay. So for a single system, now let us consider for a single system, for a single component. Let us consider theoretically. It is a water system. The P is equal to 1. C is equal to 1. The most simplest system, water system, single component. P is equal to 1. C is equal to 1. So F is equal to 2 plus C minus 1. So this is also 1 is equal to 2. So when it is ice water equilibrium or water vapor equilibrium or ice vapor equilibrium, this is a two-phase system. So P is equal to 2, C is equal to 1. So F is equal to 2 plus 1 minus 2, that is 1. So degree of freedom is 1. Again, when the three are in equilibrium, the three phases are in equilibrium, that is triple point. So C is equal to 1, P is equal to 3. So F is equal to 2 plus 1 minus 3 is equal to 0. So in this way we have applied the Gibbs phase rule to calculate the degree of freedom. Now let us see whether for a one component system the four phases can coexist. If four phases can coexist, say C is equal to 1, P is equal to 4. Then F is equal to 2 plus 1 minus 4 is equal to minus 1. So degree of freedom is minus 1. The degree of freedom cannot be negative. Okay? So for a single component system, the four phases cannot coexist. Okay? So for a single component system, four phases cannot be coexist. And we have that single phase system, that is a sulfur system, sulfur rhombic, sulfur monoclinic, sulfur liquid, sulfur vapor. So this is also one component system and there are four phases, and already we have verified for a single component system these four phases cannot coexist. So this implies there must be more than one triple point, and we will read this system separately in the near future, in the future classes. So let us now summarize. Today we have discussed the Gibbs phase rule, that is F is equal to 2 plus C minus P, and we have P max is equal to C P max is equal to C plus 2 and the F max is equal to C plus 1. F max is equal to, this is C plus 1. Okay, these three relations we have discussed, that is when the degree of freedom F increases, the P decreases, and when F decreases, the P increases. Okay, and so you can say when the phase will remain constant, the component is directly proportional to the degree of freedom. If component will increase, then the degree of freedom will increase. So we have certain relations and formulas in our conclusion for remembering, and in my next video we will solve some more problems to correlate the basic concepts, that is phase, component and degree of freedom, for better understanding before giving the entry into the depth of the phase rule. I hope you will enjoy this video, and if you enjoy this video, you share among your friends and give a like to my video. Thank you.